Okay, fine. We'll start today's class. We'll be studying the counter design, which we have started in the previous two classes. So in this class, we'll see some additional examples of designing the counter, especially the random counter design, which we have started in the last class. We'll be continuing with the same, and we'll see how we can design the random counter using SR and JK flip-flop, because already we have done so many examples using D and T flip-flop. You should know how you can do the counter design using SR as well as JK flip-flop. So we'll start with this example, right? So it is asked to design this irregular or a random binary counter using JK flip-flop. Means we need to have a count sequence like 1, 2, 5, and 7. So the maximum count here is 7. So obviously we have to go for 3-bit counter. But when you say 3-bit counter, it will have a total 8 different count sequences. But here we will not be having all 8 count sequences. That's why it is called as irregular counter or a random counter, right? This is what these people, they don't join on time. Fine. So this is the a random counter that we have to design. So we need to use 3-bit because the maximum count sequence what we need is 111, that is 7. So normally 3-bit counter will count from 0 to 7, that is 000 till 111. But here we don't want all the 8 count sequences. We want these irregular count sequences, that is 1, 2, 5, and 7. So how do we start the designing of this? The same process what you have used for designing the regular counter or the random counter, which we have studied in the previous class. Exactly the same procedure you need to use here to design this counter using JK flip-flop. Since we are going to use JK flip-flop, every JK flip-flop will have 2 inputs. So accordingly, you should use the excitation table of the JK flip-flop and you can construct the table. So first you have to write the present state, what is the next state, and then to achieve that next state from the present state, what should be the flip-flop inputs that you have to derive. Once you get all the flip-flop inputs, you should get the expression for each of the flip-flop input by solving the K-map, and then finally you can draw the logic diagram, right? So here I have given you the excitation table for the JK flip-flop. You can see 00 is 0x, 01 is 1x, 10 is x1, 11 is x0. So what are the counts we need here is, we have 001, that is 1, 2, 5, and 7. Here in fact I have not shown the other count sequences. If you want, you can show the other count sequences, and for those count sequences you can write the don't care. That is also possible that you can do it. All right. So here you can see here 001. If it is a present state, next state is 010. For 010, next state is 101. For 101, next state is 111, and for 111, the next state is 001. So that is 001 is right. So we have Q0, Q1, Q2. So far we used to take A, B, C. Here I have shown the states as Q0, Q1, Q2, and this is Q0 plus 1 or Q0 plus Q1 plus Q2 plus. That is the next state. So now you need to derive the inputs. How you will derive the inputs? You can take one by one. See here, Q2 is 0 and Q2 plus is 0. So use this 0, 0. What you should get? 0x. So write here 0x. Similarly, next is 0 and 1. So for 0, 1, what you have? 1x. So write here 1x. Then next you have 1, 1. For 1, 1, it is x0. So write x0. So you have again 1 and 0 here. So for 1 and 0, it is x and 1. So write x and 1. Similarly, for this you should take this and this you should compare. 0, 1, it is 1x. Then 1, 0, it is x1. Then 0, 1, you have to write 1x. if you remember this excitation table, very easily you can get this flip-flop inputs. So right, so like this, similarly this and this should be compared using this table, and write down that here. Lastly, like 1 1 here, that is x0. So we got the flip-flop input J2 K2 J1 K1 J0 K0. Now we have to solve 6 K-maps, each of these flip-flop inputs. One K-map for K0, then another for J0, one for K1, J1, another for K2 and J2. Total 6 K-maps you have to solve. But while entering into the cells of the K-map, since we have not written all the states here, we have written only 4 states. So for these 4 states you can enter, and for remaining you can enter the don't care in the K-map. So this is 001. So for 001 you have to enter what? Say for J2 0. Then for 010 you have to enter 1. 101 it is X. 111 also X. And the remaining 4, apart from this, whatever the input combinations you are having, for them also you have to enter X in the K-map, and then you have to solve the K-map. You can see here, these 4 I have entered 01XX, that is 001, 010, like 001 is 1, then 010 is X, like that you have to enter, and the remaining you have to enter on X, and then you can form a group like this. You will get one quad, right? Then similarly you can form for J1. So if you see J1, you have to write this. What you have to write J1 is, see 1X 1X corresponding to these 4, and the remaining 4 you have to write X. So all will be X except these 2 1. So you can form an octet like this. So it becomes 1. Similarly, J0 also you can get from that previous table here. This you take J1, right? K1, then J0, K0 you can put. So for J1, K1, J0 you will get 1 only, because here 1X you are having, remaining 4 are X. So you can solve these 6 K-maps, and you get J2 as Q1, J1 as Q1, J0 1, K0 Q2 bar, K1 1, and K2 Q1. Now using these equations, you have to draw the logic diagram. So when you want to draw the logic diagram, first thing you have to draw 3 JK flip-flops, show the clock, and then you have to connect these inputs what you have got through these equations. So you can see here 3 JK flip-flop, J0, K0, J1, K1, J2, K2 is shown, and a common clock is given. So it is a synchronous design. And then you can see here what you have, J0 equal to 1. So connect J0 to high, or it should be connected to plus VCC, right? This should be connected to plus VCC. K0 is Q2 bar. See this K0, from where you have to take, this is Q2. This is Q2, so this is Q2 bar. So take this Q2 bar and connect to K0 like this. J1 and K1 is 1. So J1, K1 both should be connected to high. Then J2 is K2. So J2 is output of this, right? J2 is equal to, sorry, J2 and K2 are Q1. J2 and K2 are together, they are connected to the output Q1. So these equations which we have got from the K-map, accordingly we have done the connection, and this gives the designing of the random counter shown using JK flip-flops. I hope all of you understood this. Any doubts here? Is it clear? Right. The important thing here is you should know how to write this particular table, which we call it as a synthesis table of the counter. You have to write the present state. Only 4 I have shown, remaining I have not shown for the simplicity. Remaining, if you encounter, you have to write the next flip-flop inputs as don't care, because for the remaining 4 cases, the next state will be don't care, because we are not going to use those 4 states. Only these 4 states are used, right? If you recall the previous example, I have shown all the 4, you can see here. This was the example here where we have 1, 2, 3, 4, 5. 5 states were there. But here I have not written 5 states, I have written all 8 states. And for the 3 which are not there, I have shown don't care. So you can do like this also, the example which I have shown. If you are comfortable with this, you can go ahead with writing all the 8 states and write the don't care for the states which you are not using, or if you don't want to write all the states like this, what we have done, you write only the states which are used, and the remaining by default when you are writing the K-map you have to put don't care. So both way you can do, whichever way you are comfortable with, you should do it, and you can design the irregular or the random counter. I hope it is clear how to do designing of a random counter using JK flip-flop. So any doubts here? Any of you are having any doubts, you can ask. Because these examples, counter design examples are very important, and you can expect 1 or 2 counter design examples for your third CIE, which is to be conducted next week. So I want all of you should go through this designing. You should able to do the designing of the counter using any of the flip-flop. It could be D flip-flop, T flip-flop, SR flip-flop and JK flip-flop. Again, I am repeating, you will be getting minimum 2 counter design examples in your third and the last CIE for this semester. Yeah, any doubts before I proceed? If you have any doubts, you can ask. All of you understood this or no? Yes, Aniket, is it clear?
Yes, sir.
Kiran?
Yes, sir. Clear, sir.
Any doubts? Ankita? Yes, Ankita, are you there?
Yes, sir.
Understood or no?
Understood, sir.
You have to practice all these examples. Whatever I have done, only these examples are more than sufficient. Right? I want all of you should do this practice for your third CIE. As I said, you will be getting examples which are covered in the class. Okay? Okay, I'll proceed further. Now, if you want to design the same counter, but you can see it is again a counter with like some states missing. If any missing state occurs, you have to go to the reset state. It is not like the earlier state where we have only the limited states. Here also we have limited states, but if any other state occurs, by default, the next state should be 0. Then such counters are called as self-correcting. They comes in the self-correcting category of the counters. How we can do the counter design either by using again SR or JK flip-flop, right? Because if one of the unused state occurs, it should go back to the beginning. That is what is called as the reset state, right? So actually this is the mod 6 example. When I say mod 6, it will count from 0 to 5. 0, 1, 2, 3, 4, 5. Total 6 states are there. Then what about the remaining 2 states? When the counter goes to 110 and 111, for these 2 states, it should come back to the reset state. The next state for these 2 states is the reset state, that is 0, right? So how we can do the designing of such counters where if the unused states occurs, you should go back to the reset states. And such counters, as I said, they are called as self-correcting or self-starting counters. So we'll see how we can do the design. Again, the procedure remains same. You have to write the present state, next state, flip-flop inputs. So self-correcting modulo 6 or mod 6 counter we have to design. And if any unused state comes, that means 110 and 111 occurs, by default it should lead to the beginning state, that is 000. So step 1, this is the timing diagram. This is the state diagram we have. Now you have to write the present state and next state. You can see here it is a mod 6. So we have 0, 1, 2, 3, 4, 5. 6 states are used, but these are the 2 unused states. So if the counter goes to unused state, what should be the next state here? You can see 00. So by default, 101 will go to 0 because of the natural count sequence. But when 110 and 111 occurs, these 2 are the unused states. When these 2 unused state occurs, then also the counter should go to the next state as 0. So far what we have done, if any unused state occurs, we used to write XXX, that is don't care. But now in self-correcting counters, we are not writing it as don't care, we are writing it as the reset state, that is 0 state. That is the only difference, rest all thing remains same. Now again here instead of Q0, Q1, Q2, I have represented it as AN, BN, CN, then AN plus, BN plus, CN plus. So you have to check again the excitation table for the JK flip-flop. 0 0, it becomes 0x. Similarly 0 0, again 0x, then 0 1. See, this is 0 0 again, that is 0x. And then for 0 and 1, it is 1x. Then for 1 1, it is x0. Then for 1 0, it is x1, and 1 0 again x1, x1. You have to write like this. Similarly, compare this and fill these two columns. Then compare this and this using the excitation table of JK flip-flop and fill these two columns. And finally, we got the 6 flip-flop input JA, KA, JB, KB, JC, KC. Now for all these 6, you have to use 6 3 variable K maps, and you have to get the equations for this. These are the 3 variable K maps shown. How you write, it doesn't make any difference. You can write from this side like ABC or ABC, but you have to be consistent. If you are starting here, this should be AB. You can't write A, B and C here. So it is AB like this and C, because you are coming in this direction. If you go in this direction, then you can write A here, and then you can write BC. Accordingly, you have to fill the cells of the K map and get the expression for JC, KC, JB, KA, JA, KB. These are the equations we have, and the last step is using these equations, you have to draw the logic diagram again. Again, you have to show 3 flip-flops. You can use positive edge triggered or negative edge triggered. In this case, which flip-flop we have used? Whether it is a positive edge triggered flip-flop or negative edge triggered flip-flop?
Negative edge.
Yes, anybody? What kind of flip-flop we have used here?
Negative
edge. Of course,
edge.
all 3 are JK flip-flop, but whether we have used positive edge triggered or negative edge triggered flip-flop, that depends on what. You can see how we have shown the clock. How the clock is applied? Clock is shown with bubbles. So it indicates it is which edge flip-flop? It is called as
Negative edge triggered.
Negative edge triggered JK flip-flop. So whether it is negative edge triggered or positive edge triggered, the functionality remains same. Only thing, state changes occur either with the rising edge of the clock or falling edge of the clock. If you show positive edge triggered, state changes will take with the rising edge of the clock, and if you show negative edge triggered flip-flop, state changes will take place with the falling edge of the clock. This is the step 6 and the last step in designing the counter using JK flip-flop. Both these examples which you have seen today are same. Only difference is in the first example, if any unused state occurs, we have written don't care. Whereas here in self-correcting counters, if any unused state comes, we will write it to the reset state. Next state will be the reset state, that is 0 0 0. That is how we can do the designing of the counter. So this you can do it as a homework. Design a mod 4 irregular counter with the following count sequence. It is a modulo 4 counter 0 0 1 0 1 1 0 1. Right? It is a mod 4 counter, but the count sequence is not 0 1 2 3. It is 0, then it is 2, then 3, and then 1. So it is again called as irregular or random counter. So mod 4 counter you have to implement, but not in sequence 0 1 2 3. That's why it is irregular or random. So how many flip-flops required now? How many bit counter it is? Yes? How many bit counter it is? And how many flip-flop you need? How many bits are there in each of the count sequence? You can check there. Yes? Each count sequence is of how many bits? Yes, how many bits are there in each count sequence? I don't know, you people are understanding this counter design or not. So many classes I have spent on this designing of the counter only. You can see here it is 2-bit, no? Every count sequence is of 2 bits, 0, 0, 1, 0, 1, 1, 0, 1. So it is 2-bit counters. That means you need 2 flip-flops. So you can see here, I can show that the present state can be denoted by this. This is present state. This is next state. And these are the flip-flop inputs. Which flip-flop we are using? D flip-flop. So you have only 2 inputs. Again, if you use JK or SR, you would have got 4 inputs. So 0, 0 is going to 1, 0, 0, 1 is going to 0, 0, right? Because you can see here 0, 1 is going to 0, 0, 1, 0 will go to 1, 1, and 1, 1 will go to 0, 1. I have written here 0, 0, 0, 1, 1, 0, 1, 1. According to the state table, you have to write what is the next state. And one good thing is here is, since we are using D flip-flop, whatever the next state you are having, same thing you have to write it as a flip-flop input. 1, 0, 1, 0. So here it is 1, 0, 1, 0, 0, 0, 1, 1, 0, 0, 1, 1. So using D flip-flop is very simple. Then you have to write K-map for each of these flip-flops, that is DB and DA. So we get DB equal to A bar, DA equal to B. Then you can draw the diagram. Very simple. 2 flip-flops you have to show, flip-flop A, flip-flop B, right? The first flip-flop D, that is DA, is what? AN bar. Sorry, DA is BN. So this is DA. This is flip-flop D. DA is B, right? B is given. And what is DB? DB is Q bar. That is AN bar. That means output of this is bar. So this AN bar you should connect here. This you connect. That is simple design, right? Just within 2-3 minutes you should be able to do the design if you are using D flip-flop, right? So like this, there are so many examples are given here. Just I want you people to go through this. This is the lab experiment which you will be doing in your lab, right? Then some of the examples. I want you people to design this counter, mod 6 counter. This is what given. I just you can work out and you can get the K-map. Same thing is explained. I don't want to go into details again. Same procedure you have to use, and you can draw the logic diagram for the list. So with this, we have seen the designing of the counter. So to summarize what we have discussed, just I have put in this slide the difference between the asynchronous and the synchronous counter. Already I have explained it in the very first class when we started our discussion on the counter. Just at the end of the counter, again I have taken this slide so that you should know the difference between the asynchronous and the synchronous counters. So what you can see there is, in asynchronous counter and synchronous counter, already I explained, just go through it, what you need to do for up counter, down counter, how the clocks are applied, right? That is the major difference between the asynchronous and the synchronous counter. And also I told which is complicated and which is simple. Synchronous counter, directly we are applying all the flip-flops will get the same clock, but they are a bit complicated. Asynchronous counter design is simple, but there we need to connect the output of one flip-flop as a clock to the next flip-flop, right? Then you can have, the problem can be solved by different method, like modulo 3 down counter I have told. You can use either SR flip-flop, JK flip-flop, T flip-flop or D flip-flop, and you can do the designing of the counter, right? These are the different ways in which you can do the designing of the counter. Present state, next state you have to write, and based on which flip-flop you are using, you have to write the flip-flop inputs. See, if you use SR flip-flop, you will get total 4 inputs. If you use D flip-flop, you will get only 2 inputs. If you use JK flip-flop, again you will get 4 inputs. And if you use T flip-flops, you will get again 2 inputs. So all these flip-flop inputs you are going to get by using what is called as excitation table of the flip-flop. So you should know the excitation table of the flip-flop, and using excitation table, you can do the designing of the counters. Then you have to use K-map. You can see this particular example is solved by all the ways. Different methods or multiple methods are used. Different flip-flops are used. So if you use like SR flip-flop, 4 K-maps you have to use. If you use D or T flip-flop, only 2 flip-flops are 2 K-maps are sufficient. Similarly, if you use JK flip-flop, you need to use 4 K-maps, and then you can draw the diagrams using these equations which you have got. That is a simple, actually. Counter design is a very simple method, provided you have understood the concept of what is called as excitation table, present state, next state concepts. If you know the present state and next state and the excitation table, very easily you can design anything and everything using any flip-flop, right? So before we move on to the next part of this chapter, one more important thing, you should know the difference between combinational circuit and sequential circuit is explained in this particular slide. You can see combinational circuit, there is no feedback or there is no memory. Sequential circuit is combinational circuit plus memory element becomes a sequential circuit. That is the major difference between the combinational circuit and the sequential circuit. So all the differences between combinational and sequential circuits are listed here. You can just go through this. Anyway, I'll be sharing all these PPTs with you so that you can just go through it, and you have to work out. Just by reading the design example, you will not get the confidence. So you have to take the pen and paper, you have to solve, you have to do the designing, then only you will get the confidence of designing any counter, right? So with this, we have come to the end of the counter design. So if you have any difficulties, any doubts in this, you can ask before we proceed further. Because next part we have to discuss is the registers. Already you people have studied this in your first year engineering course. What do you mean by a register? Can anybody define what is register? Okay, just I'll give the introduction of the register, and the actual register concept we will study it in the next class. Can anybody define what is register? It is REGISTER, not RESISTOR. There is a huge difference between RESISTOR and REGISTER. Can anybody define what is register?
So it is a group of flip-flops used to store binary information.
Very good. It, as rightly said, group of flip-flops which are used to store the binary information is called as a register, because you know that a flip-flop can be used as a single bit memory element or a storage element. If you use one flip-flop, it can store only 1 bit of information. But when you want to store multi-bit of information, then you have to use cascading of multiple flip-flops, group of flip-flops, and these group of flip-flops which are used to store the binary information are called as registers. So registers are used to store the binary information. So the most suitable flip-flop to implement register is obviously the D flip-flop, because we know that in D flip-flop, whatever input you give, same thing it will store into it. Whenever you give D input as 0, and if the clock is applied, 0 will be stored in the flip-flop, and whenever you give D input as 1, and if I apply the clock, 1 will be stored in the flip-flop. Therefore, D flip-flop is most suitable flip-flop to implement register. It doesn't mean that you can't use any other flip-flops to implement registers. You can use any flip-flop to implement register, but the most suitable one, most suitable candidate to implement register is the D flip-flop, right? Because you know that any flip-flop can be converted into any other flip-flop. It is possible to convert JK flip-flop to D flip-flop, SR flip-flop to D flip-flop, T flip-flop to D flip-flop, and vice versa. And that is the reason why you can use any flip-flop to implement either the counters or the registers. In counters also, we have seen you can implement the counter by using any of these flip-flops, either D, T, SR, and JK flip-flops like this. We can implement the registers using any flip-flops, but the most suitable, as I said, is the D flip-flop. So there are various types of registers, like the normal registers which are used to store the binary information into it, or we have a special registers which can shift the information stored into it either to the left or right, and such special registers are called as shift registers. So shift registers are used to shift the binary bits stored in the register either to the right or to the left bit by bit, one bit position at a time, and those registers are called as shift registers. So you can either shift left or shift right, and depending on how you are storing the data in the shift register and how you are retrieving the data, we have 4 different types of shift registers. And those 4 different types of shift registers are called as serial in, serial out shift register, serial in, parallel out shift register, parallel in, serial out shift register, and parallel in, parallel out shift register. There are 4 different types of register: SIPO, SISO, PISO, PIPO. These are the 4 different types of shift register, depending on which how you are storing the data and how you are going to retrieve the data stored from the register. We have these 4 different types of shift registers. So in this part of the module 5, we have to discuss about the register, simple register, how they can be used for storing the data, and then we will be discussing some applications of registers, like how registers can be used as the adder with accumulator concept. Instead of going for the serial adder, we can use the parallel adder or as well as serial adder concept. How we can do that, that will be discussed. And then in the end of this module 5, we will be discussing about the finite state machines, like Moore machine and Milli machine, and what is the difference between the Moore machine and the Milli machine. So those are the things we will be discussing in the next class. So before we close for the day, if you are having any difficulties, you can ask me, and I'll show you what all thing we are going to discuss in the next class. We are going to discuss about this simple register implemented using D flip-flop to store the data, having load facility, right? Then how we can implement this same thing with the enable signal, then the symbol of the 4-bit register, then data transfer between different registers. These are just examples for the simple register. Then we'll be studying parallel adder with accumulator, how we can implement a parallel adder with the accumulator so that we can accumulate the result in the accumulator register, right? And this is the block diagram for the same. And then we'll be discussing about the shift registers, which I explained just now: serial in, serial out, parallel out, serial in, parallel out, and parallel in, serial out. These are the shift registers which I have discussed already in your first year engineering. Again in detail in the next class, I'll be explaining this, right? So this is also important from your examination point of view, and whatever I will be discussing till the next class, that will be there for your third CIE. That means the register and shift register concept will be there for your third CIE test conducted next week. So up to all these, this anyhow you have studied, just need a revision, which I will be doing it in the next class. So whatever I will be discussing in the next class, as I said, that will be there for your CIE test. These are the shift registers, special universal shift register also. We can perform shift right, left, timing diagram, all these things. Then how we can construct a Johnson counter from the shift register and the ring counter from the shift register. That's what we are going to study. And then we'll be studying about the what is called as the sequential machines called Moore model and Milli model. So till this point, you will be having for your third IA test this Moore and Milli machine, and this part, whatever is there, that will not be there for your third IA test. Also, very little part is left in the module 5. We'll be discussing in the next class, and that will be there for your third IA test. So if you have any difficulties, you can ask before we end the today's class. Any doubts, any difficulties you have? Yes?